Welcome to my lecture on moments, centroids, and centers of masses. So I want you to imagine that we have a balancing condition for two masses. The center of mass here in this diagram with mass 1 at a distance x1 from x bar and mass 2 at a distance x2 from x bar has to satisfy the balancing condition, which is that mass times x bar minus x1 is the same as the mass 2 times x2 minus x bar. And here x bar represents the center of mass. Okay. Now what I'm going to do is, since we want to determine where the center of mass is, we're going to solve the equation for x bar, which represents the center of mass. When I do that, I just FOIL mass 1 and I FOIL mass 2. Okay. Then I move everything involving an x bar to the left-hand side, and I move m1 times x1 to the right-hand side. Now I obtain this equation here. I obtain this one, where right there, and all I do is I divide by the total mass, m1 plus m2. So I get this equation, x bar is equal to m1 x1 plus m2 x2 divided by total mass. Now, I can represent this with more than 2 point masses, and the way that this simplifies is it's the summation of mi(xi) divided by the sum of all the masses. This is called the moment about y. Divided by the total mass. Okay, so that's how I find the center of mass with just one single dimension. But I want us to consider this example where we have masses of weights 2, 5, and 6, and they're placed at the points 3, 2, minus 1, 1, and minus 2, 1. I've drawn them here on this graph for us. Okay. Now notice this is not one dimension, but it's two dimension. So the balancing point is given by x bar, y bar. Here y bar, we need to satisfy the balancing condition in both x and y. So y bar is nothing more than the balancing condition, sum of masses times yi divided by total mass. Okay. So I just need to repeat this balancing condition twice, and that's my center of mass. Okay, so my balancing point in the y direction, that's going to be the mass of 2 times the y value of 2 plus the weight of 5 times by the y value of minus 1. Plus the weight of 6 times by the y value of 1. Okay, and then we divide by the total mass. Total mass is going to be 2 plus 5 plus 6. Okay, and so that denominator, that's going to be 13. This numerator, well, we have to figure it out. So we're going to have 2 times 2, we'll get 4, minus a 5, plus a 6. Okay, so I think this will be 5/13. And this is our center of mass in the y direction. Now we need to repeat this in the x direction because the center of mass is both in x and in y. So this is going to be the summation of mi times xi from I equals 1 to n. So there's only 3 points, so we'll do this 3 times divided by total mass. Now total mass we've already calculated. That's 13. Mass times x, so this is going to be 2 times 3. Then we're going to go to the weight of 5, and it's going to have a negative 1 for its x value. Then we're going to go to the weight of 6, and it's going to have a negative 2 for its x value. And we need to figure out what this is. Okay, so we're going to get 2 times 3 is 6, a negative 5, and a negative 12. So I think we'll get minus 11/13 in x and 5/13 in y. And that is our center of mass. So our center of mass here is going to be minus 11/13 and 5/13. Now, that was for discrete points. I want us now to find the center or centroid of the mass given by this region. So it's y equals x squared, x is 0, x equals 1, and y equals 0. And this produces an area. Now this area has a weight because it has a density. Okay, so think of it as being a metal. And I'm going to shade this metal, shade it red. Okay, then I have to delete it because I need to draw some diagram. So imagine that this is completely filled and it's like a metal or something like that. Our goal is to find the center of mass or centroid. Okay, so now let me erase this. Okay. Okay. So there's a key idea here. The center of mass of this object, which is a rectangle, is in the center. So that is, it's going to be this point right here. And if this has x1 and this has x2, then this is x bar. X bar is nothing more than x1 plus x2 over 2. So its center of mass is going to be x bar. Well, then I'm going to call it center of mass y bar. That's the average of the height there. Okay, so y bar is the average height. Okay, and one other thing, because we'll need to know this, is that the total mass is given by density times area. After all, rho is the mass per area. And if I know how much area is, I know what the mass is. Okay, so in general, that's going to be rho times the area, and the area is given by integral from a to b of f of x dx. So this is going to be rho times this integral from 0 to 1, right, of f of x is x squared, and this evaluates to be rho over 3. Now, we have seen that the center of mass in x, this is going to be m sub y divided by total mass. Now, we know what total mass is. That's going to be rho over 3. Now, all I have to do is find m sub y. That's all that I need to know. M sub y, well, its definition is going to be the sum of mass of an object times by distance of an object. So mass times distance of an object. And I'm going to put this from I equals 1 to n. So what I'm going to do here is I'm going to divide up the x-axis. So here's going to be x sub I and x sub I minus 1. Okay, then I'm going to take the average. The average is going to be right there. Okay. And I'm going to inscribe a rectangle. A shocker, I know. And I'm going to treat this rectangle as being a slice, okay? And so one thing that you should notice is that I'm going to treat this whole rectangle as just a point. And so I'm going to inscribe many of these rectangles, and I'm going to calculate the moment about the y-axis for all of these little points, taking the rectangles to be smaller and smaller. That is, I'm going to have this limit as n goes to infinity for m sub y there at the bottom. Okay? So I think what I'll have here is I'll have this limit as n goes to infinity, the summation from I equals 1 to n, and mass of a rectangle, well, that's going to be the density times the area. The area of this rectangle, right, keep in mind that this height is given by f of x bar, okay? So the coordinates of this point in the middle is x bar and f of x bar over 2, okay? So let's get this straight. There's one more dimension we have, which is a delta x. Delta x is the width of the rectangle. So the mass is going to be the density times the area. The area is going to be f of x bar multiplied by delta x. Okay. The distance in the x-axis is nothing more than x bar. Okay. After all, that's the distance from 0 is x bar. That's the center. We're treating it as a point. Okay. And when I do this, I can clean this up, and I'm going to get this limit as n goes to infinity of the summation from I equals 1 to n of rho times by f of x bar times by x bar, and then multiplied by delta x. Well, I have three ingredients here, an x bar, a limit, and a summation. So I can write this as this integral from a to b of rho times by x multiplied by f of x dx. And that's how I calculate my moment about the y-axis when I do not have a discrete set of points. And it's quite a simple idea here is that, or the key idea here is that the center mass of a rectangle is in the center, and I'm going to inscribe lots of rectangles inside this mass. Okay. So when I do this, I'm going to pull the rho out in front. This is going to be the integral from 0 to 1 of x times by f of x, which is x squared, and this is going to be rho over 4. Okay. So I can go back, I can calculate x bar, and it's going to be rho over 4. Okay. And as you can see, the rows cancel, and I'm left with 3/4. So we don't even need to know the density. We just need to know the shape of this object, and it needs to have constant density. So x bar is 3/4. Let's go ahead and calculate y bar. So remember, y bar is going to be m sub x divided by total mass. Remember, total mass, that's going to be this rho over 3. And m sub x, the moment about the x-axis, this is given by this is going to be the summation of all the little points, which are rectangles now, of m sub I times by y sub I, the distance in the y-axis. Okay, and I'm going to put this limit as n goes to infinity there, okay, just for good measure. So I'm going to have this limit, n goes to infinity. The mass here excuse me, the mass here, the mass we've already calculated is going to be rho times by f of x, the height of that rectangle, times by its width. So all we're going to do is we're going to take this rectangle that I described in the curve. It has area given by height times width. The height is f of x bar, the width is delta x. So the area is going to be that f of x bar times by delta x. And then we multiply by rho to get mass, okay, because that's the density. Now y sub i is nothing more than the height. This is y sub I. Okay, that's the height of the rectangle. Okay, so those two are the same. So I'm going to replace this by f of x bar. Okay. Excuse me. That y sub I is not that y sub I there. I apologize. That y sub I is given by this. This is going to be x bar, comma, y bar, and this is y sub I. That's what it's referring to. Because we're referring not to the height, we're referring to the center of the mass, okay, which is in the center. And y sub I bar, that's going to be f of x bar divided by 2. So I apologize there. This is f of x bar divided by 2. And that's m sub x. Okay. Now I have three ingredients here that change my life. So let me rewrite this one more time. Okay, and I apologize, I forgot the sum there as well. And so this is going to be rho, and I'm going to put the 2 there, rho over 2 times f of x bar squared multiplied by delta x. Okay, so because I have this limit, I have the summation, and I have a delta x, I get to write that this is an integral from a to b of rho over 2 multiplied by f of x bar squared dx. Okay, and in our situation, a is 0, b is 1. I'm going to leave rho alone, and in all your problems, you can just ignore rho, the density, because it will cancel with the area. And f of x bar, okay, well, x bar is just a symbol, so usually we just drop the bar there, so I apologize. And we're just going to have f of x. Okay, that's going to be x squared multiplied by dx. Okay, and this will evaluate to be rho over 2, integral from 0 to 1, x to the 4th, because that's squared, dx. And this will be rho over 2 times by 1/5. So this will be rho over 10. Okay, so now we have the moment about x. We have that this is rho over 10. The rows cancel. This is going to be 3/10. So our center of mass in this case, that's going to be 3/10 in y. And in x is going to be 3/4. Okay. And that's how we find the center of mass for a solid region. And one thing that you should note is that you can typically ignore the density rho because it's not needed to find the center of mass. Okay, thank you for joining me.